to one of the last steps in the development process. Imagine in the last few weeks, months, or maybe even years, the application has been implemented, including a highly optimized algorithm partially written in assembly. The entire program has been extensively tested and debugged. In short, time and money has been spent by you or your employer, and you would like to protect the intellectual property when the ready product is shipped to the customer. What prevents this customer from downloading the program right out of the flash and analyze it, or even worse, sell it on his own? Apart from malicious intent, you would like to make it harder for potential attackers to disassemble the program and study its implementation. For this purpose, the log bits are introduced. They can be set to prevent any download or alteration of the non-volatile memory, and in this chapter we will talk about how to set those log bit fuses. There are multiple protection modes available depending on the application. For instance, instead of only preventing a flash download, do you also want to prevent any upload and/or update of the program located in the flash? For that, different log bits exist, and in the first half of this chapter we will talk about those. Once the bits are set, only a complete chip erase will unlock the chip. It sounds drastic, but we already did it many times in the exercises, probably without realizing it. In the second half of this chapter, this topic will be handled. Let's get started. First, we have to understand that there are two different instructions for accessing and modifying the flash. The first one is SPM, which is the assembly mnemonic for store program memory. Its purpose is to erase and alter the pages in the program memory. This instruction is executed every time when a new program is uploaded through the bootloader. It also sets the log bits. The assembly instruction LPM, meaning load program memory, is the opposite of SPM. It reads the data from the program flash and also the fuse and log bits. We already used it in the flash section when, for instance, the fuse is read to determine the size and location of the bootloader. And before diving into the log bits, we have to remember that the flash is divided into two sections: the application section and the bootloader or boot flash section. While the size of the bootloader can be configured via the boot as Z fuses, and hence the space this bootloader occupies in the bootloader section is configurable, the section size itself remains constant. Depending on in which section the LPM or SPM instructions are executed, different rules apply. If the developer would like to protect the application section, boot log bit 0 protection mode needs to be considered. In this mode, SPM and LPM instructions are considered whose target address to write to or to read from is located in the application section, here circled in red. In BLB0 mode equal to 1, there are no restrictions, and LPM and SPM instructions physically stored anywhere in the flash can alter or read from the application section. In the second mode, no modification of the application section is allowed anymore by SPM instructions in both sections. That means that, for instance, a bootloader located in the boot flash section cannot update the application section any longer. But also the user program just lost write access to the same section. In the more restrictive mode 3, no instruction in the bootloader section has access to the application section any longer. Any existing bootloader is not able to write nor to read the application section. Besides being unable to update the user program, essentially that setting also turns off any download or verification through the bootloader. On the other hand, the user program is still able to read its own instructions. But since it cannot be altered, and probably the software developer does not communicate the flash content through, for instance, UART, the application is protected by now. And last but not least, the fourth BLB0 mode. In this, the bootloader is still unable to verify the application section, but it is allowed to send a new update to that section, while there are no restrictions on the LPM and SPM instructions as long as they are located in the application section. Okay, that was the protection about the application section. The same modes also exist for the bootloader section. Now again, the LPM or SPM instructions are physically located in either of the two sections, but the address they operate on is located in the bootloader section. What restrictions are available here? First, no restrictions at all. That means the bootloader can update itself or can be updated from the application. But it also can be verified, since the data can be read by LPM. Again, I can disable all modification access to the bootloader section if the BLB1 mode is set to 2. Hence, if BLB0 that we had earlier and which targets addresses of SPM and LPM in the application section is set to 2 as well, the entire flash becomes read-only. If BLB1 mode 3 is active, only the bootloader can verify itself, but again, it cannot alter anything. And the last mode, it states that no LPM executed from the application section will be able to read any address in the bootloader section. But any SPM can write to that section. That allows the update of the bootloader from the application and from the bootloader itself, but the application will not be able to verify that update. In the previous slides, we always talked about updating the bootloader. For instance, in this slide, the application can update the bootloader we just said. However, that is not entirely correct, as the bootloader can be smaller than the bootloader section. Therefore, to say it correctly, in BLB1 mode set to 4, any address located in the bootloader section, no matter if that address is occupied by the bootloader or if it is just application data, can be written to but not read from. Please refer to the chapter Flash and EEPROM in the ATmega available in this course to see how data is written to the non-volatile flash from the application. Okay, now we know what modes do we have, but we do not know where those bits to configure BLB0 and 1 modes are located. To set the BLB0 and 1 addressing both sections in the flash, bits 2 to 5 located in the lock bit fuse need to be modified. By default, all bits are set to 1, that means unprogrammed, which is somewhat counterintuitive. BLB1 and BLB0 bits unprogrammed means that no restrictions are applied, and for both sections mode 1 is selected. Also note that these bootlock bit modes are only available for the ATmegas and are not present in, for instance, ATtinies. As we can see, there are 2 more bits which we have not talked about yet. Those 2 least significant bits are just called lock bits. And what is their meaning? They allow us to encode 3 more protections. If both fuse bits are unprogrammed, that is set to 1, no restrictions are applied. In lock bit mode 2, the flash is write protected but can still be read, and for instance avr-dude is able to verify the flash content by downloading and comparing it against another binary. In LB mode 3, even that is no longer possible. While the BLB modes allow a fine-grained access policy for applications running in the different sections of the ATmega, the lock bits are designed to address the programmer and debugger attached to the chip externally. Please note that if the flash is locked, the hardware debuggers introduced in the previous chapter do not work anymore. Otherwise, that would defeat the purpose if the flash content could still be downloaded through, for instance, the debugWIRE interface. Since the fuses and their values can be a bit confusing, it is always advisable to confirm the desired settings using an online fuse calculator. In this course, I introduced 2 of those calculators so far, but only one shows the lock fuse. The link is attached to this lecture. Conveniently, the calculator already shows the parameter that we have to use for programming the fuse through avr-dude right here. However, please note that there is an update regarding avr-dude. The version in the VirtualBox image throws out a warning that setting the fuse to FF will not be supported in the future anymore. The reason is that the 2 most significant bits of the fuse are unused. Hence, the maximum value that the fuse accepts is 3F in hexadecimal format and not FF as shown here. Okay, imagine you extracted an ATmega from an appliance that does not work any longer. Unfortunately, the program has been locked, but in your hands is a perfectly working ATmega and you would like to repurpose it for your own projects. Can you reset the lock fuse? Yes, you can. Once the lock fuses are set, they cannot be removed anymore. To reset the lock bits, a complete chip erase needs to be performed. First, a chip erase deletes all content in the flash and EEPROM. Once that is complete, the lock bits are reset. Do note that a chip reset is not a factory reset. The high, low and extended fuses remain unchanged. So if the wrong clock bits have been chosen in one of those fuses, those wrong settings remain. The EEPROM can be exempted from the chip erase to, for instance, preserve data stored there. To exclude the EEPROM from the process, the fuse EESAVE in the high fuse of the ATmega 328P needs to be programmed. Otherwise, the content of the EEPROM is not preserved. How to perform a chip erase? Actually, that is pretty simple. Executing avr-dude just with a question mark parameter reveals the supported options. We have the part number, baud rate, configuration file and programmer that we used numerous times during this course. The D parameter is an interesting one. If it is not provided to avr-dude, every time a new program is uploaded to the MCU, automatically a chip erase is performed. So it seems we already did a chip erase many times, and avr-dude even informed us that it does so in the status messages when it starts writing to the flash. Have a look at the output of avr-dude in the previous exercises and check if you can spot it. There are a few more parameters that we already know, and here is the E option, which just performs a chip erase. Hence, with all the standard parameters specifying the MCU, the programmer, etc., if a -E is added, the chip is erased. No -U to specify what is to be reprogrammed with which data is needed. This -E blanks out the entire flash. The log bit fuse is set like any other fuse. After choosing the desired modes, specify the new value in the -U parameter. Here we would like to write to the log fuse the value 3C in hexadecimal format. The M indicates that this value is a real value and not, for instance, a file name. And that is all what I have about the log bits. They reduce the attack surface and hence increase the effort an attacker has to invest to obtain the program from the flash tremendously. In the exercise, you have to try it once. Take, for instance, the blinking LED example and protect it. A programmer should not be able to upload another program nor to verify the existing blinking LED program. Once you completed the exercise, I will see you in the next chapter. Thanks for watching.